Greetings ladies and gentlemen, welcome to the demonstration video for my microcontroller course project. For this project I've chosen to implement a so-called falling sand game. A falling sand game is a simple grid-based physics simulation where users can place different types of elements and see how they behave and interact with each other. My implementation of this simulation uses a 128 by 128 unit grid and implements 4 different elements, specifically stone, water, plants, and fire. The video quality of the first few clips is a bit rough until I got used to the improvised recording setup, but does improve rapidly. Let's get started. The user interface of the simulation is extremely simple. On the display there is a cursor with a white outline. The inner color of the cursor indicates which element is currently selected. To move the cursor, the user can use the joystick on the left of the control pad. To place cells or elements, the user presses the top right button, and to delete cells, the user can press the bottom right button. In order to toggle between different elements, the user can press the middle joystick button. Here I'm creating a small stone structure by holding down the top right button and moving the joystick. I then move the cursor to the top left of the display, click the middle joystick button to move to the next element, in this case water, and press and hold the top right button to generate water pixels, which then flow downwards and fill up the structure. As you can see, the water pixels behave as one might expect. They flow when there aren't any barriers in the way and fill up the entire volume of the little containers in the structure. I then click the middle joystick button again to move to the next available element, plants, and generate a small section of plants towards the bottom right of the simulation. And now I generate more water to demonstrate the interaction between plant pixels and water pixels. When water pixels come into contact with plant pixels, there is a small chance that they are replaced with plant pixels. This brings us to the next type of element, specifically fire. Fire spreads through plant pixels, again with a certain probability, and then dies out in the next iteration. And here, to show another interesting behavior of the water simulation, I'm first creating a stone container and then filling it with water. Here we see the water generating small waves and turbulence as it settles. And next we poke a small hole in the bottom of the container. And just like real life, the water flows out through the bottom of the container. This implementation of the water simulation comes with a small quirk. The simulation grid is updated from bottom to top and then from right to left. A result of this is that water likes to flow from left to right. A simple way to avoid this type of behavior and perhaps make the simulation more realistic is to randomize the order in which pixels are updated. We see this version of the simulation running. A problem with this, however, is that this is far too viscous and takes much longer to flow, and also doesn't look as good. In this case, I chose to sacrifice realism for aesthetics and fun, and kept the original simulation. The update order randomization is, however, still available in code, and if you read the source code, there are instructions in how to reactivate that. You just need to uncomment one line. Here is a demonstration of the joystick movements. There isn't only directional inputs, but also acceleration on the joystick, meaning the further you push a joystick in a given direction, the faster it moves. The educational booster pack contains a number of peripherals, including sensors, such as a light sensor, an accelerometer, and a temperature sensor. Here I'm creating a container filled with water to show how the accelerometer is used in the simulation. We turn the device upside down, and then the flow direction of the water changes to match gravity. Next, we demonstrate the effects of the light sensor on a group of plants. If it becomes too bright for the plants, then there is a small chance that they start to burn. And yeah, those were the main features of my little simulation. I'm quite impressed with the RP2040, specifically that the entire simulation of about 16,000 elements could fit in RAM, and that the processor speed of 133 MHz was enough to provide a quite fast frames per second. I'm relatively happy with how my project turned out, but there are some areas that could be improved. For instance, the light sensor is read during every simulation step. This could probably be more efficiently implemented as a hardware interrupt. If a desired light threshold is reached, then the interrupt could be triggered. Thanks for your attention. I hope you found it a bit interesting. And of course, don't forget to like and subscribe.